are quite useful when it comes to algebraic structures, because the binary operation in question may be some type of map. And now, since among the algebraic structures that we defined is a group, you can be asked to show that a given set and a certain composite map qualifies to be a group. So in relation to the mappings we discussed and our group discussion, I would like us to have an illustration. You recall we had we checked for some properties on the commutative property, whether the or a composite map is not commutative, and we shall be able to illustrate this in some specific examples. So before we can get to illustrate, now to use the concept of various types of maps that we discussed in relation to the algebraic systems, I would like us to mention very briefly what we mean the concept of Cartesian products, and now the concept of relations, because a relation can also be viewed as an operation on a set. So we will go straight to, I'll share my screen. Entire screen. I'm trying to share my screen there. I also want to start recording. I've just noticed that I didn't share. I think I shared the class video on WhatsApp, but I've realized I put it on the LMS. And the good thing is that the groups which were missing in LMS were added last evening, so I'll be able to post most of the material there on the learning platform, on the learning management platform. So what I would like us to very briefly mention is the Cartesian product of sets. This is familiar from set theory, your knowledge on set theory. I'll clear this from our previous class. So from set theory, the concept of Cartesian product is not new. So Cartesian products. So this borrows quite heavily from our knowledge on the XY axis, where we have the x-axis and the y-axis, and we normally give points on the Cartesian plane. We call this the Cartesian plane, and we give points in form of ordered pairs, x, y. And on the Cartesian plane, it is understood that when we give the coordinates of a point as x, y, it is understood that x is the x coordinate and y represent the y coordinates, or rather x. Now, if you do this from set theory, x is a member of set x and y is a member of set y. So we can say that as a point, or rather points, points on the Cartesian plane, on a Cartesian plane, are usually read. They are usually read using rectangular coordinates. Using the rectangular coordinate system. As a set of ordered pairs of this form, e.g. pairs of the form, say, AB. So we shall start, you see, when we read now coordinates of a point in the Cartesian plane, we normally understand that the first value is the x coordinate, the second value is the y coordinate. So we shall define an ordered pair. We start by defining an ordered pair. What do we mean by an ordered pair? And for this, we can say that an ordered pair, let me just have it at the top there. Definition, ordered pair. We can say that an ordered pair is a set containing, say, an ordered pair is a set containing exactly two elements, for which it has been decided, which is the first in the pair and which is the second in the pair. So it has been decided which is the first and which is the second. In that pair. And that is why I said the coordinates of a point, like if I take the coordinates of a point xy, it just comes automatically that I will know, this being the coordinates of a point, the first value is the x coordinate, the second value is the y coordinate. So in the Cartesian plane, the way that pair of coordinates is written has been decided that the first value in the pair will come from the x-axis and the second value will come from the y-axis. So when you have such sets containing of those pairs of points, then we call it an ordered pair. We call that an ordered pair which contains exactly two elements, and it is known the first one will come from this set, the second one will come from which set. Next, we define the Cartesian product of two sets. Another definition, we can say that the Cartesian product the Cartesian product of two sets, say A and B, of two sets A and B, is the set of all ordered pairs, is the set of all ordered pairs. Now we know what an ordered pair is. All ordered pairs, say AB, where A belongs to set A and B belongs to set B. And we denote the Cartesian product and is denoted by A cross B. So that is what we call the Cartesian product of sets A and B. We denote it as A cross B. So symbolically, we can say that we can represent this as A cross B is equal to the set of points of the form A, B, such that A belongs to the set A and B belongs to the set B. So that collection of points, this one, represents the order, the Cartesian product of A and B. Then you will find that if, for example, we revise the order, if we reverse this order, let me continue up there. If we have the set, the Cartesian, if now we want the Cartesian product of B and A, B, the Cartesian product of A, B and A will be the set of ordered pairs BA. Note we have reversed the order now. BA such that B is from set A, is from set B. B comes from set B and A comes from set A. So again, you can see now this operation is not commutative. So you will find that in general, B cross A, because now these points may not give the same results depending on how the operation or how the sets are defined. So we can say in general, the Cartesian product is not commutative. In general, A cross B is not always equal to B cross A. Because you can see, even the way we obtain their ordered pairs, it is different. When you reverse the order in which the two sets have been multiplied, you reverse the order in which the pairs of points will be obtained. For example, e.g., suppose we have two sets. Suppose the set A has elements 1, 2, 3, and B has elements A, B. Then we can have this set. Then the set A cross B that is the Cartesian product of A and B, will consist of these pairs, these ordered pairs. They'll be in the form AB, where A is from A and B is from B. So we shall have these pairs, 1A, 1B, 2A. The first entry is from set A, the second is from set B. 2B, 3A, 3B. So that collection of points represents the Cartesian product of A and B. You can see throughout all the pairs, the first element is from set A and the second is from set B. But now, if, for example, we reverse that, to obtain the Cartesian product of B cross B and A. So B cross A will be the collection of these points. The first entry will, the first element in the pairs will come from B, and the second will come from A. So we shall have points of this kind. A1, A1, A2, A3, B1, B2, B3. So you can see now the pairs of points. These points in B, in the Cartesian product of B and A, are different from the points in the Cartesian products of A and B. And that is why we can now clearly see, even from this specific example, that A, the Cartesian product of A and B, is not equal to the Cartesian product of B and A. Those pairs of points are different. So that is now the Cartesian product as an operation. You can easily show that this is not commutative. So we can say that in general, we can say the Cartesian products in general, Cartesian products are not commutative. In general, Cartesian products are not commutative. And that's what we have shown. Next, we define the term, another terminology that is now a relation. We can say something about relations on sets. By relations here, we look at situations. Okay, in general, if you were to use a layman's language, a relation is there are some family ties or something of between two people. When you say that this person is related to the other person, then it means that there's some tie, something in common between them. So now, in sets of real numbers, the types of relations we look at are relations like those operations that relate two numbers, like equal to, less than, is the square root of, is the square of, etc. So those are the relations we talk about in as far as sets are concerned. We don't talk of now relatives like parents and sisters and siblings and friends. So I want to say something about relations here, but now this time with reference to sets or with reference to mathematics. Relations. So, in as far as families are concerned, a relation is a tie between some two people or some relation, just the same as the word suggests. But now in sets of real numbers, the types of relations we consider are, for example, say equal to, less than, greater than, maybe we can have a square of, or the squares, a square, a root, and so on. So those are the kind of relations we refer to when now we are in referring to sets in mathematics. So we can say that those relations that involve two elements are called binary relations. So we can also say that relations involving two elements are called binary relations. And no wonder when we are defining an algebraic system, we've always talked of a set together with a binary relation. But now when we are representing a relation per se in notation form, we normally represent them in form of pairs. We represent them in form of pairs, whereby the pairs, it is known that the first element in the pair, where it comes from, and where the second element in that pair comes from. So we can consider this, for example, consider the set of integers. Consider the set of integers with relation let's say, I'll put the relation in quotes here, is the square of. Is the square of, using ordered pairs, such as, now if you were to represent that relation in ordered pairs of this kind, then we have this. The relation is the square of, this is the relation, is the square of. So in ordered pairs, we shall have pairs like this, like 4, 2. 4 is the square of 2. We can have another pair, 4, negative 2. 4 is the square of negative 2. 36, 6. 36 is the square of 6. Also, we can have 36, negative 6. 36 is the square of negative 6, etc. So these pairs, all of them obey the relation that we are having. So the relation is the square of. So the first number is the square of the second one. So we can have this to indicate an integer and its square. To indicate an integer and its square. So we can now indicate this kind of relation in general as follows, whereby the first one is the square of the second. So we can say that this can be indicated by, in general, can be indicated by this ordered pair, n squared comma n. So that the first entry in the ordered pair is the square of n, and the second one is the n itself, where n is an integer. Where n is an integer. And we note that we can now see that since the squares of integers are also integers, then we find that these pairs, or those ordered pairs, belong to the set which is the Cartesian product of z cross z. So notice that this pair, n squared n, belongs to z cross z, the Cartesian product of the set of integers by itself, whereby the first one is the square of z, the square of n is also another element of z, and n is an integer. So we find that relations are represented in form of ordered pairs. But now, the rule that governs that relation must be stated or must be known. The rule is normally known, and then now you can generate ordered pairs that satisfy that rule. Another definition, let me just clear all. Another definition when we have a binary relation from a set A to a set B, that becomes a subset. It is actually a subset of the Cartesian product of A and B. So a binary relation from A to B is a subset is a subset of the Cartesian product. Now we know what the Cartesian product is. Of the Cartesian product A cross B. And that's what that's why we have said that n squared n, the ordered pair n squared n, is we also found from the illustration we have found that the ordered pair n squared n is belongs to this Cartesian product of z cross z. So this is in agreement with what we have found from our example. Then now, some other terminology I want us to define in relation to, or in connection to relations. We can define now the domain and the range. You see now, this is where we are obtaining the set on which the relation is applied, the set where the relation is applied. So I want us to define some terminology there. We can say that the domain of a binary relation, the domain of a binary relation is the set of all the first elements. It is the set, of all the first elements in the ordered pairs. In the ordered pairs. In the ordered pairs in the relation. In the relation. And the range, let me continue up there. And the range is the set of all the set of all the second elements in the ordered pairs. In the ordered pairs in the relation. So we can say that we can denote now the domain and the range as follows. We denote domain by D of R, where R is the relation, and the range we denote it by small r of R, where R is the relation. So we have the domain of R and the range of R. The domain is the set of all first elements in the ordered pairs of the relation, and the range is the set of all the second elements in the ordered pairs of that relation. For example, I hope the screens are still sharing. I'm seeing the numbers there. Is BSS, are you in? Are we having BSS and BMC? BSS and BMC on the public chat, let me know if you are there. Seeing 205, 205. BMC, BSS, because I shared this link to BSS as well. BSS, are you there? If they are not there, I'll follow up with their rep, wondering why they are not in this class. BSS. Okay, so let's continue. So we have the domain and the range of a relation. Then we can illustrate this with an example. If we consider two sets, say S and T, and we want to write down the Cartesian products of S and T, and then now from that Cartesian product, we shall also describe or define a relation on that set. On that set, a relation of a relation we shall define some relation. So let's consider. I want to illustrate this with some example. I want to start from the top there. So, example, we can take two sets. We take two sets S and T. So let S be the set 1, 2, 3, 4, and Y and T be another set with elements, say 1, 2, 3, 4. So the Cartesian product then S cross T will be this collection of points. We shall have 1, 1, 1, 2, there are many, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, then 4, 1, 4, 2, 4, 3, and 4, 4. So all this collection represents the Cartesian product of S and T, with S given as that and T as that. Now I can describe a relation between S and T so that I consider the relation S is less than T. Supposing I define my relation R as S is less than T. Let me continue here. So we define a relation R by S is less than T. Let's say that is my R. S is less than T. Then I can represent all those pairs that represent my R. Then I still want, I want to squeeze that relation here so that we can compare. Then we have there. Then my relation R will comprise of these ordered pairs. The element from S is less than that from T. So those pairs will look like, I'll take all those pairs from S cross T that satisfy the first element is less than the second element. First is less than second. So I will circle with a different color the ones that satisfy my relation R. These two do not satisfy. 2 is less than 3, 2 is less than 4, 3 is not less than 2, 3 is not less than 1, 3 is not less than 3, 3 is less than 4. 4, all the others do not satisfy. So my relation R will comprise of these pairs. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. 2, 4, and then sorry, this one more that I'm leaving out. Then we have 3, 4. So those are the pairs that are found in R, where R, the relation R is S is less than T. So, and you can see all these are subset of S cross T. You can find all of them in the Cartesian product of S and T. So in this case now, I can make another remark. Sorry. I can make another remark here. Since we have obtained all the members of R from S, then we can conclude and say that indeed R is a subset of S. R is a subset of S cross T, of that Cartesian product. So that is in agreement with what we have said earlier. And then now, supposing I want you to find the domain of R. What will be the domain of R? Domain of R, as R, when R is defined this way, is the set of all first entries in the ordered pairs. So the domain of R will comprise of elements 1, 2, and 3. And the range of R, let me have it down here. The range of R will comprise of the set of all the second elements in those pairs. So we shall have the range as 2, 3, 4. So depending on how the relation is defined, you can obtain its domain, you can also obtain its range. Another example, supposing now in the same set S and T, suppose now we vary our R and now we use a different relation, say the equals, the equality. I hope you can recall what our S and our T was. And now I want another illustration here where let R be the relation S is equal to T. Remember our S was the set 1, 2, 3, 4. T was also the same set 1, 2, 3, 4. Those are our two sets. S is equal to T. This is capital T. So then, the relation R will comprise of ordered pairs xy or small s small t such that S is equal to T. That will comprise my R, which we can write as, where S is equal to T, I will have the ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4. Those are the pairs that will satisfy the relation R. And now, what is the domain of R in this definition now? Domain of R is the set of all first elements. So will be the set 1, 2, 3, 4. And the range of R is the set of all second elements. So we have again 1, 2, 3, and 4. Supposing my R now to be less than, I want, we already had the less than. I want R to be, I'll give you an exercise where now I want R to be, the relation R to be greater than, S is greater than T. So as an exercise, obtain, now this is an exercise. The domain, let me just use the notation, domain of R and range of R where R is this relation. The relation ST such that S is greater than or equal to T. Is greater than or equal to T. So you will obtain R, that is the relation R that obeys this property. And then now I want you to obtain the domain and the range of R. So in the next 1 minute, I get the domain of R and the range of R. And on the public chat, let me see some of those responses. because that now is a brief discussion of the relations that I wanted us to discuss. So I think we have, so far we have discussed most of the operations that may be found in the binary algebraic systems. So what matters is now how a question is phrased, so that you may be given a given relation or a given binary operation, and then you are asked to determine whether a set under that binary relation forms a group or qualifies to be an algebraic system. So we shall go back to the composite maps, or the composition of maps, and recall our definition of a group, because that is the first example so far we have discussed of an algebraic system. So I want us to discuss now, in view of the various other operations we have done, I would like us to discuss some examples of situations that would lead us to a group. Now let me check on the public charts what you are getting as the domain and the range. The domain and the range. No screen seen. How come? I'm still sharing. So if you cannot see a screen, go to the top and refresh your screen. These are an arrow, a circular arrow up there. Please, when you click on that, your screen will be refreshed. You'll be able to see, because I am still sharing. Okay, so I am seeing there some responses on the public chat. Domain of R. Somebody is asking the domain and range is Nifanane na ya previous question. The relation, let's go back to our relation. Our relation R here is S is greater than T. So the pairs are such that the first element is greater than the second element. So, and remember my S, the two sets have elements 1 up to 4. So we are saying that S is the set 1, 2, 3, 4. T is the set 1, 2, 3, 4. And now my R is defined as ST such that S is greater than or equal to 4. S is greater than or equal to 4. So equality is accepted and now greater than. So my ordered pairs will look like this. S, I can have 1, 1 for equality. I can have 2, 1. I can have 2, 2. Sorry, yes, 2, because I am strictly obeying the equal to or greater than condition. 2, 2. Then 2, 3 will not belong here because 2 is less than 3. So I need where the first entry is greater than the second one. So 2, 3 will not work there. 2, 4 will not. 3, 1. 3 is greater than 1. So we have 3, 1. 3, 2 will also belong there, because 3 is greater than 2. 3, 3, will 3, 3 be a member there? 3, 3 will belong because 3 is equal to 3. Now, 3, 4 will not belong there because 3 is not greater than 4. 4, 1. Then 4, 1 will belong there. 4, 2 will belong there. 4, 3. Again, 4 is greater than 3. And also 4, 4, because 4 is equal to 4. So those are the pairs that I will have in my R. Those are the ordered pairs we have in R. 1, 1, 2, 1, 2, 2. 2, 3 will not be there because 2 is not greater than 3, and 2, 4. Then 3, 1 is okay, 3, 2 is okay, 3, 3 is equal, it obeys equality. 3, 4 will not belong there. 4, 1, yes. 4, 2, yes. 4, 3, yes. 4, 4 obeys the equality. So those are the members we have in R. And now from this, the domain becomes D of R is now the set of all first elements. So we have 1, 2, 3, 4. The domain, not the domain, the range of R is the set of all the second elements. The set of all the second elements. So we have 1, 2, 3, 4. So again, 1, 2, 3, 4. So there we are. I want you to now obtain the domain and range where the equality here is not accepted. So that one I'll leave you to do on your own. So you can call this one, sorry. For 2, we can say obtain the domain of R and range of R where R is the relation ST such that S is greater than T. So that one you can do it as an exercise. That we can do as an exercise. Now I want to say something concerning a composite map. And I want us, because this is because I will give an assignment. I'll post the assignment on the LMS for you to work on. But before we can do that assignment, which I will expect you to do and submit still online. I understand you are trained how to submit assignments online. So we want to have an assignment that you will do and you submit on the online platform. Now, supposing we have a set and an operation, a transformation operation that maps it in the following manner. So I want to have this as a question. Although this is a question we shall do together, show that the set G composed of, say, F1, F2, F3, and F4 of the four transformations transformations of the set is C of complex numbers on itself, defined by F of 1, F1 of Z is equal to Z. F2 of Z is equal to negative Z. F3 of Z is equal to 1 over Z. And F4 of Z is equal to negative 1 over Z for every Z in the complex set. So we want to show that this, I hope you are writing that question, because it's a question I want us to work together, and then it will help you sort out some assignment. So we want to show that this is an abelian group. You remember we defined an abelian group. So this, we continue up there. Is an abelian group with the composite operation. The composite operation. The composite operation. In other words, I want you to show that G together with the composite operation, that where G is the set F1, F2, F3, F4, And the mapping that we are, or the operation, the transformation operation we are referring to is from the complex set, and F is mapping from the complex set to the same complex set. So we want to show that this is an abelian group. So remember now, when we talked of a group, there are the 4 axioms, the basic axioms of a group, but now being an abelian group, we must test for all the 5, including the commutative property. So in this one, you need to, since F has been defined in various ways, I would like you to try and complete the Kiley table. The operation there is the binary, the composite operation. The sets we are working with are F1, F2, F3, and F4. So we have that on both columns, F3, F4, and we want to complete that table. So F1, the composition of F1 composite F1 of Z, from the definition of the composite map, is F1 of F1 of Z. And from our definition, F1 of Z is Z. So F1 of Z is Z, so this becomes F1 of Z, which is equal to Z. So here, you will write it in terms of the Fi's. So F1 gives us Z, and Z is F1, so we will have F1 there. F1, F2, from the definition, it's important to write down those, how the various F's are defined. So F1 of Z is equal to Z. F2 of Z is defined as negative Z. F3 of Z is defined as 1 over Z. F4 of Z is defined as negative 1 over Z. So F1, composite F1 of Z, is from the definition of composite map, is F1 of Z. F1 of Z is Z, so it's like having F1 of Z, which is equal to Z itself. So the result of F1, composite F1, is F1. F1, composite F2 of Z, I'm just illustrating here so that now in the same way you continue and finish. You continue and complete that table, the Kiley table. So we have F1, composite F2 of Z, from definition is F1 composite, or F1 of F2 of Z. And from the definition, F2 of Z is equal to negative Z. So we have F1 of negative Z. F1 is equal to, F1 of Z is equal to Z. So F1 of negative Z will again be equal to negative Z. And negative Z is F2. So this becomes F2. This is equal to F2. F1 composite F3 of Z becomes F1 of F3 of Z, which is F1. F3 of Z, F3 of Z is 1 over Z, so F1 of 1 over Z. And for F1 of 1 over Z, our Z now here is 1 over Z, will be 1 over Z. And 1 over Z in terms of now the functions that we are having is F3. So F1, F3 gives you F3. F1, F4, you can check in the same way, work them out the same way to complete that table. So we are completing the Kiley table for this mapping. Then now we check against the group properties if all the group axioms have been satisfied to qualify it as an abelian group. So we are working on that table, the Kiley table. So I am working on mine on the side here. F2 of Z is negative Z. 1 of negative Z is that. So we are still working on the question. So I'm hoping that you are also working on it. I'm working on mine as well. F2 of F3 of Z. 3 of Z is 1 over Z. So F2 of 1 over Z. Is 1 over Z. So we are still working, and then we shall post the complete table. So work on yours as well. F2, now F3. One F3, 3 F1 of Z, 3 of Z, Z is Z. Yes. Sorry. We are working on the table, on the Kylie table. Maybe I should put it in a better form.
Okay.
But this is what we are doing. We have a table.
Yes.
The composite, the binary operation is there, is the composite map. The sets F1, F2, F3, F4, F1, F2, F3, F4. Our set G has these 4 elements. Then now, the composition will be as follows. F1, F2, F1 composite F2, F1 composite F1, that is the intersection of the first and the first column, the first row and the first column of Z is F1 of Z. And by our definition, F1 of Z is equal to Z. So this is like having F1 of Z. Because F1 of Z is Z, and F1 of Z is equal to Z. So in terms of the elements of G, F1 of Z is Z. So this Z here is equivalent to F1. So in my table here, I'll place F1 there. And I do the same, F1 composite F2. I'm trying to fill the first row of that table of Z, which is F1 of F2 of Z. Which is equal to F1. F2 of Z, I hope you have written those mappings somewhere. F2 of Z is negative Z. So we have F1 of negative Z. And F1 of Z is Z. So in this case, our Z is negative Z. So this result will be equal to negative Z. And negative Z is equivalent to F2. So this is F2 there. F1 composite F3 of Z is now F1 of F3 of Z. F3 of Z from our definition of F is 1 over Z. So this will be F1 of 1 over Z. But F1 of Z is Z. So our new Z here is 1 over Z. So F1 of 1 over Z is just 1 over Z. And 1 over Z is F3. So we have F3 there. Likewise, in a similar way, you can show that the last one there will be F4. For the second row, if the second row, let's see if this is what you got. F2 composite F1. So row 2 row times column 1, F2 composite F1 of Z becomes F2 of F of Z, F1 of Z, which which, since F1 of Z is defined as Z, we have now F2 of Z, because F1 of Z is Z. So we have F2 of Z, which is equal to F2 is defined, F2 of Z is negative Z. So this will be equal to negative Z. And negative Z is equivalent to F2. So this is equivalent to F2. So there I will have F2. Then F2 composite F2 of Z. So that is what we are doing to complete this table. So F2 composite F2 of Z from the definition of the composite map is F2 of F2 of Z. F2 of Z, we know it as negative Z. So this becomes F2 of negative Z. F2 of negative Z, F2 of now negative Z will be negative negative Z, which is equal to positive Z. And positive Z is F1. So this becomes F1. So the result of F2 here is F1. F2 composite F3 of Z becomes F2 of F3 of Z from the definition of the composite map. F3 of Z is defined as 1 over Z. So this becomes F2 of 1 over Z. F2 of Z is negative Z. So since our Z here is 1 over Z, F2 of 1 over Z becomes negative 1 over Z. Negative 1 over Z is equivalent to F4. So this, in the table here, we shall have F4. And that's what we are doing now to complete the remaining part of the table. So we have F2, F3 is equal to F4. And then you continue now, F2, F4. I've not yet finished that, so you can continue working on. So F2, F4 of Z is equal to, and when you get your result, you post it on the table and we complete the entire table. So just continue as I work also on mine. So once you have completed worked out all the entries of the table, you complete that Kylie table. So are we done with the table? So the question we were trying to answer is to show that the set G composed of F1, F2, F3, and F4 is an abelian group. And then the transformations defined on that set are F1, F2, F3, F4 are given. So we are to show that G under the composite operation is indeed an abelian group. So you can check. Let me fill out what I obtained from my calculations. The Kylie table will look like this. The second row is F2, F1, F4, F3. The third row is F3, F4. You can check F1 and F2. And the fourth row is F4, F3, F2, F1. So check if the table you have obtained looks like the one I have shared. That's what that's what I have obtained by working out those compositions, just the same way I have illustrated here, but now working for all the possible combinations in G. So now, looking at the table, the curly table we have there, we can see all the elements inside the table are members of G. So clearly you can say that clearly closure property, we can see that the first property we check is closure. So from the table, the binary operation in G is closed. So we can say from the Kiley table, from that Kiley table, G is closed under the operation is one, under the composite map. G is closed under that binary operation of the composite map. So the first property is satisfied. What about the second one? The associative property. If you take any three members of G, do they obey the composite property? If I take three members of G, do they obey the composite map? So if we take, for example, F1 composite F2 into bracket composite F3, will this be equal to F1 composite F2, these two into brackets composite F3? Will they be equal? So if you look at F1 composite F2, sorry, F2, we work the brackets first. F2 from the table, F2, let me have this. The intersection of F2 and F3 is this one. So we can say here F1 composite F4. Because now this is the F4. This gives you F4. The composition of F2 and F3 is F4. So now you have F1 composite F4, F1 composite F4, F1 F4, F1 F4 is F4. So you have F4 on the left side. This other side, F1 F2, F1 F2 is F2. So you have F2 composite F3. F2 F3, F2 F3 is F4. So you can see this left side is equal to the right side. And you can do this for any, you can combine them in any form. So we can say here number 2, the associative property. The associative property holds or is satisfied. Then property number 3 for abelian group is the existence of an identity element. By identity element, if you go by the definition of identity, it is that element which leaves each member of the set unchanged. So if you look at the first row, F1 acting on each of the members of G does not change it. Or if you look at the first column, F1 acting on each of the members of G does not change it. So we can say now, we can say that number 3, existence of identity. So there exists the identity element E, and the identity element E is F1. So because of that existence of identity element E, then we can say that there is an identity element in G. The other property, number 4, is existence of inverse element for each member of G, for each F in G. So for each member of G, do we have an identity element? And we check this by concept, since we have said that our identity element is F1, for each row or column, which we look out for F1. So F1 exists there, F1 appears there, F1 appears there, F1 appears there, meaning that the inverse of F1 is F1, inverse of F2 is F2, inverse of F3 is F3, inverse of F4 is F4. So each element in G has an inverse in the same set G. So each element in G has an inverse. So number 4 is also satisfied. What about now the commutative property? Property number 5, property number 5 is now the abelian property. Property number 5 is the commutative property. You check if it is satisfied. And remember, when we looked at the Cayley tables and the various binary operations, we said that a set is commutative under a binary operation if corresponding rows and columns are identical. If you can notice or observe that corresponding rows and columns are identical, then the commutative property is satisfied. So if you look at the elements of row 1 and column 1, the elements of row 2 and those of column 2, they are identical. They are identical. So we can say that for this one, we can say corresponding rows and columns columns are identical, and hence this binary operation is commutative in G. And now, having shown all the axioms of an abelian group are satisfied, then we can now conclude and say that, therefore, the set G, together with the binary operation of this composite map is indeed an abelian group. So in conclusion, we can say that therefore G, together with the binary operation composite, is an abelian group. And that is what we were asked to show. That was our task, to show that this is an abelian group. So as I said earlier, various operation, as long as you have a set and a binary operation on it, and we have defined the various binary operations on sets, then it is possible to show that that set or that algebraic system qualifies to be a group, or qualifies to be an abelian group, or qualifies to be a semi-group, qualifies to be a monoid. All the algebraic systems we have discussed so far, it is possible to show that a given system either qualifies or does not qualify to be that particular algebraic system. So as I said, I will post some assignment for you to do, and then you will submit, and I'll go through it, so that now next week we shall look at some more. There are some two types of groups that I would like us to discuss. So we shall do that next week. So for today, I think we will call it a day, and thank you for attending. So have a good afternoon.